Welcome back. This is the second part of the lecture on how to scale a cell to increase capacity. Here, we would be analyzing the different trade-off associated with different options for scaling. Much of engineering is about analyzing the trade-off. So this is an important aspect of battery engineering. So in the previous lecture, we had taken a particular cell of particular chemistry, um, and then we had derived the volume of the cell. So there are contributions from the negative electrode, from the positive electrode, from the gases that are evolved, and the separator, current collector, and so on. So we have derived this equation. The question which we want to address is the following. Supposing we have an initial design of a particular capacity. I want to increase the capacity, this quantity, by 2x. That is, I want to make another battery, another cell specifically, with twice the capacity. I have different options. For example, I can just increase the thickness of the active material without increasing this area, cross-sectional area. The other option can be I can have the same thickness of the active material, but increase the cross-sectional area. So what I want to analyze is what are the changes in volume associated with this option and with this option. So, for example, first let us analyze the option 1, wherein I do not increase the cross-sectional area. That is, this remains the same, but I'm just increasing the thickness of the active material. So with this option, what is that I'm changing? I am changing only these quantities without changing any of these quantities. So this seems to be very advantageous. In fact, if you analyze this option, the change in capacity, for example, when I move from 10 to 20, along with this change in capacity, increase in volume would be the least with this option. That is, without increasing the cross-sectional area, only increasing the thickness would only affect these terms and would result in the least amount of volume change. This looks very desirable. Let us analyze further. The expression for current density is as follows. If we increase the capacity, I'm increasing this term. And while increasing the capacity, I want to keep the discharge time the same. And as I said, I'm keeping the cross-sectional area also the same. So with this, what would it amount to is my current density will almost become twice as much when I increase the capacity. As you probably know by now, increasing current density has other consequences. It increases the activation over potential, ohmic over potential, and also the concentration over potential. This would have significant consequence. For example, we want to operate the battery only to a particular voltage. Okay, so you do not want the battery voltage to go beyond or below this particular point. So there's a particular cutoff voltage associated with a particular battery. So if we increase the over potential because of these constraints, because of the constraints associated with option 1, I may reach the cutoff voltage more quickly. So this is quite undesirable. So this option does not look all that great with respect to how quickly I would reach the cutoff voltage. There are other issues also. For example, in this option 1, I have increased the thickness without increasing cross-sectional area. So when I do that, it is quite possible that there is going to be non-uniform deposition of the solid products in the porous carbon. So not all sections of the porous carbon will be uniformly deposited and uniformly utilized. So there can be greater deposition of the solid product in one of the region, and this is going to significantly affect my current distribution. So this non-uniformity has to also be accounted for when we increase the thickness. So option 1, even though it appears as if we have the least increase in volume, has other consequences which are not desirable. So let us look at the other option, wherein I keep the thickness the same. I do not have any change in thickness, but I increase the cross-sectional area so that I can get twice the capacity. So this is what we mean by option 2. Let us first understand this option. In terms of volume, what is the term I am affecting? I'm mainly increasing the cross-sectional area to get increase in capacity. When I do that, my volume would tend to increase because I'm increasing this quantity, but other consequences. So what is the consequence? When I increase this cross-sectional area, there is a potential drop to get the current from the current collector, current out from the current collector. Okay, so as the cross-sectional area increases, this ohmic drop also increases. So what I would see is that even though I'm having this option 2, the increase in volume is more than the increase in volume due to option 1. In addition to increase in volume, I have other consequence of increase in ohmic drop associated with current collection via the current collector with larger cross-sectional area. To address this issue of ohmic drop in the current collector, what I may do is that I may increase the thickness of the current collector to decrease the resistance. Okay, so if the thickness of the current collectors are increased, what it would amount to is it will compensate for the increase in the current resistance of the current collector. But if you remember, the current collector in this battery chemistry is the negative electrode itself. So when I increase the thickness of the negative electrode, current collector for the negative electrode, I am also increasing certain other quantities. Therefore, that should also be taken into account. So it is true that by increasing the thickness of the current collector, I'm able to decrease the resistance, but it would also amount to increasing some other components, which would again increase the volume of the cell. So this is, even though this occurs, it has a consequence in terms of volume. This is the option 3, but this is in a way the most reliable way of operating the cell. So what do we exactly mean by trade-off? By trade-off, what we mean is that we may gain something. While we gain something, we are losing something. What is that we are gaining in this third option? Third option involves not only increasing the cross-sectional area, along with cross-sectional area to an extent, along with an increase in cross-sectional area, to decrease the resistance, we are also changing the thickness of the current collector. All this is going to improve my battery performance. That is a gain. But what is the loss? It is going to have significant increase in the volume of the cell. So this kind of analysis is very, very important in battery engineering. This is something that you should become skilled at if you want to analyze a trade-off associated with increase in battery capacity. There is another option wherein we have cells as a stacked assembly. So instead of having just increasing the cross-sectional area, I can have the increase in cross-sectional area in a different manner. So just contrasting. Okay, so see, in the previous option, I just increased the cross-sectional area. There was increased ohmic drop. Instead of doing that, I can have a stacked assembly, because here also I'm increasing the cross-sectional area, but the current collector, the distance or the cross-sectional area of individual current collector is not increased. Okay, so the twice the cross-sectional area is obtained by having two current collectors in this manner. So this is also advantageous. So this option would fall, the volume increased with this option would be similar to option 2. So what we should be looking at when we analyze trade-off is we should be able to represent the trade-off quantitatively. So analyze the terms associated with increase in cross-sectional area, terms associated with increase in thickness of the current collector, terms associated with these quantities. So that is why it is first important to have a reasonably quantitative expression. In this case, the expression was associated with the volume of the cell. So when we want to increase the capacity, there are different approaches to increasing the capacity. So what are the consequences of the different approaches has to be analyzed quantitatively. That's what we try to do in this lecture. In the next lecture, we will look at a different topic, electrode and cell design to achieve a particular rate capacity. That will be taken up in the next lecture. Thank you.